about set, and it was like, okay, it's like I have a set and I can have some objects in that, and there is no need that those objects are from the same area. They can be like numbers, all letters, or like numbers and letters and words and many other things. So for example, 1 and B and apple is one example of a set. You also remember the cardinality of that set or size of that set is the number of elements which are there, which is 3 here. Also, we talked about Pn or power set, which is the set of all the subsets. Let's see, what are the subsets here? The subsets are different than the elements. The elements here are 1, B, and apple, but the subsets, I'm going to write all subset in that big set which creates P of n. It can be like empty set, and then a set of 1, a set of B, a set of apple, or any set which contains any 2 of them, which you see it will be like 3 choose 2. Now you know that because you know combinatorics and counting. So 1 and B is another subset, 1 and apple, B and apple. And finally, I have all 3 or the whole set S. I can write it as S, or I can write it as 1 and B and apple. So what we see here, or let me, okay, close that here. What we see here is that here I have all of these, which is 8 subsets. So if I want to talk about cardinality of P of n, actually let me write it as P of S because it is power set of S, and it is the size is equal to 8. Actually, if the number of elements is equal to n, then or let's say in S again, and then I use P of S is equal to 2 to the power of n. You remember that from the set theory, and also we showed that one in counting as well, in binomial coefficient, and it is just a reminder of all that we have learned before. So one more thing that we learned in set theory is was actually Cartesian product. Cartesian product is defined when we have 2 sets A and B, for example with 1, 2, 3, and B contains, for example, B and C, and Cartesian product of these 2 sets, like A Cartesian product, which we show that with this, the notation is this, is the set of pairs. So each element here is a pair, and that pair is ordered, which means that it is different if I have, for example, 1 and 2 or 2 and 1. They are different. We care which element comes first. So the first element of each of these pairs come from A because A is first, and the second element comes from B. And we actually write all of those pairs, all the pairs that we can have. So see, I can have 1 and B, 1 and C, 2 and B, 2 and C, 3 and B, 3 and C. So I'm going to write all of them. 1 and C, 2 and B, 2 and C, and finally 3 and B and 3 and C. Okay, so also it is just on this example, but if I want to have the formal definition, it will be like pairs using that notation. It will be pair of A and B such that A is element of A and B is element of B. You know, it is the formal definition of that. But here is actually I have two sets. So I don't have like more sets. I don't have 3 or n sets, but we can define the Cartesian product on more than 2 sets as well. Okay, so let B1, B2, and Bn are all sets. So here you see that I don't have 2 sets anymore. I have n sets, and I want to define the Cartesian product on these n sets. So what happens is that I have set of not pairs, the like n array relations. Like I have B1 and B2 and Bn, all the n array relations like this, such that B1 is element of B1, B2 is element of B2, all the way Bn is element of Bn. It is easy. Again, I care about this order and I pick one element from that, one element from that. Any of these can give me one element in the Cartesian product of all these sets. Going back to this example, you see that A Cartesian product B is not equal to B Cartesian product A, because B Cartesian product A will be equal to B and 1, B and 2, B and C, C and 1, C and 2, C and C. So we care about these orders. Okay, now that we know the Cartesian product of n sets, and also we saw that example for 2 sets, I want to define the relation actually. A relation R can be any subset of Cartesian product of some sets. So if I have like that n sets, I can define n array relation such that it is a subset of the Cartesian product of those n sets. It can contain all the elements in that Cartesian product. It can contain some elements or some of these ordered sets. So here, if I have this, again going back to this, we call them binary relations. Any subset of Cartesian product of 2 sets is a relation. Actually, it is a binary relation because I have 2 sets. And here, let me write that with red. Any, with purple actually, any subset of this is an array relation. Okay, we'll see some examples, but after that, we actually will focus on binary relations, not n array or bigger relations. So the first example we are going to see together is example 1 of your lecture note. and it is, let A is equal to A and B, and B is 1, 2, 3, and C is the set of minus sign and plus sign. The order actually is different. You know that it is the same when we are talking about sets, because sets are not order. So there is no difference if I write that as 2, 1, 3, or I write it as minus sign and plus sign. So the only reason I changed that was because I wanted to write the same as the lecture notes. But in sets, they are not ordered. But here they are ordered, and we care about that order. Okay, so here you see that I have 3 sets. And what is the Cartesian product of A, B, and C? It is, okay, you see, I pick first element from this, second from this, and third from this. So I can have A and 1 and plus, A and 1 and minus, A and 2 and plus, A and 2 and minus, A and 3 and plus, A and 3 and minus. And the same for B. I will have B and 1 and plus, B1 minus, B2 plus, B2 minus, B3 plus, B3 minus, and I'm done. You see I have all of these. And okay, one thing that I forgot to mention in the last example, I'm going to talk about that in this example. You see the number of elements I have here is 12 if you write that. So it will be the cardinality of a Cartesian product B Cartesian C is equal to 12. But how can I give a rule for that? Actually, you see here, the cardinality of A is 2, cardinality of B is equal to 3, and cardinality of C is equal to 2. What happens is that for each of these, I can choose any of these, and for each of these, I can choose any of these two. So by counting and combinatorics, you already know that it must be equal to the product of these 3 numbers, which is 2 times 3 times 2, which is again the same as 12. Here, if I want to see how many or what is the size of B1 Cartesian product B2 Bn, we can just write the cardinality times cardinality of B2 times cardinality of Bn. Okay, one question. We said we can define relations as any subset of the Cartesian product set. So here in Cartesian product, I have 12 elements. So a relation, I can define a relation as any subset of this set, right? So how many relations can I define? Since any subset of this set can be one relation, I can say the number of subsets is the same as the number of relations. So I'm going to write that here. subset of Cartesian product of some set or let's say n sets is a relation. So the number of relations as we can define on n sets let's say again v1, v2 to vn is the same as the number of subsets of v1, v2, this Cartesian product, which is 2 to the power of the cardinality of v1 times cardinality of v2 times cardinality of vn. Here, the number of relations in this example on A, B, C, the A cross B cross C is 2 to the power of 12. The reason is that the size, the number of elements of A cross B cross C is 12. So I can have 2 to the power of 12 relations. Okay, now let's see two relations that we can define. See, any subset can be a relation, but sometimes we say, okay, define a relation which has this property, and then we can call that relation. So it actually makes the relations more important, because by some properties we can define relations on that set. We don't go just create any relation and say, okay, it is the relation I want. Okay, on this three sets A, B, C, I want to define a relation R1 with the property that, or let's say such that the second element is 1 in all of them. So you see, actually this relation contains this, 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 and this. So I can define R1 as A and 1 and plus, A and 1 and minus, B and 1 and plus, B and 1 and minus. And relation R2 in this example is the one that defined by taking those triples that have plus sign in the third coordinate. So R2 has plus sign in the third coordinate. So you see here, I will have this, 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 this. So it will be A and 1 and plus, A and 2 and plus, A and 3 and plus, B and 1 and plus, B2 plus, and C1 plus, and Actually, I don't have C, right? So sorry, I got confused. Actually, it is B and 3n plus. Okay, here are our R1 and R2. Example 2 is talking about the Cartesian product of 5 sets actually, such that we have some initials which are letters, gender which can be M or F, age which can be any number between 0 and 150, eye color which is between a set of blue, green, brown, gray, and also major. And then it is talking about the actually Cartesian product of all these 5 sets, and you can see that, you can check that example from the lecture note. It is long, but it is so easy. So in the next video, as I said before, I'm going to talk about binary relations, and from the next video we only focus on binary relations because they are really important. Okay, see you in the next video.